Brief introduction to our first speaker, Urvashi Rao. So Urvashi has more than 15 years of experience in algorithm research and software development for radio astronomy. She focuses on algorithms for wide field and wide bandwidth image reconstruction, joint single dish and interferometric image combination, radio interference detection and mitigation techniques, and algorithm automation. At the National Radio Astronomy Observatory, she leads science development for CASA, which is the software package for radio interferometric data processing for the BLA and ALMA. And today she's going to give us an overview of image construction techniques in radio astronomy. So Urvashi, please take it away.
Thank you, Adam. And sharing my screen. Okay, thanks everyone for organizing this and asking Dan and I to be part of this rather interesting exercise. So today I'm going to be talking about radio interferometry, and the outline is just this. So both Dan and I have talked about this in advance, and we're going to structure both our talks to roughly follow the same outline. So we're going to introduce what images are and different ways and modalities of making images, and then hone in on one technical concept, and in my case, it is how an interferometer works. And we're going to just talk about image formation and define the inverse and the forward problems, and then summarize. All right, so let's just start. What is in a radio astronomy image? An image has pixel amplitudes, and the value in a pixel is a physical quantity called the flux density. It's a measure of the power coming from the source as measured at the antenna per unit area per unit hertz and integrated over a small patch of sky. And that's our angular resolution of the beam. So this is what's in the image. And the absolute value of this matters, which means we have to calibrate our data and instruments, because this is what will allow us to tie the number to the actual energetics of the source. So what do we look for in these images? We look for spatial structure. That's the first thing. And this is an image of the M87 radio galaxy, which has a black hole at the center, jets spewing out from it and forming all kinds of lobes and halos. And what people do with this is they look at the absolute intensity or flux density value over here and connect it to energy budgets, and you can test all kinds of physics theories once with these measurements. So the spatial structure is one thing, and then there's the time variability. And this is the same source. If you zoom in much closer, you can actually see movement of the inner parts of the jet. And of course, this turns into if you go even closer, you get the lovely image from the Event Horizon Telescope of the, What are the other things we look at in the images? Spectral structure. So the plots here are examples of what the spectra look like. So the y-axis is the same flux density and the x-axis is frequency. And the different lines show the spectral profiles for different types of emission processes. The plot on the right shows what type of objects make the different kinds of spectra. And so an astronomer will make images at different frequencies and then encode these slopes in various ways. So here is an example of the Abell 2256 galaxy cluster. And in this case, color encodes the slope of the spectrum, which then translates to the age of the source. And so what you're seeing here is galaxies basically swarming around, and the heads of the galaxies are younger than the tails, which tells you where the emission is happening and where it is trailing off and things like that. Another thing you can do is astrochemistry. So you can look at spectral lines. These are both emission and absorption lines. And so again, astrochemistry. You can also play with Doppler shifts. If, for example, there is a cloud of gas that has a certain molecule that's emitting, and if that thing is moving towards or away from us, the frequency at which we see the line is shifted. And so by making images at different frequencies, you can essentially get three-dimensional structure and movement information. And so here's an example. It's an ALMA image of the carbon monoxide emission from a shell around a star. And it's just a beautiful example of exploring three-dimensional structure in space by exploring our frequency dimension. The other axis is polarization. And in radio interferometry or astronomy in general, polarization is just the angle at which your electric field is progressing. And this gives us a lot of information about magnetic fields. That's all I'll say there. All right, so what are the kind of instruments that we have? There is what we call a single dish, which is just a dish antenna that collects the signal from the sky, and there's a single number that comes out at any given time. since it's a single number, what this represents is the integrated flux coming from a specific direction on the sky. And so if you want to make an image with a single dish, you do a raster scan. And that's what's illustrated at the bottom left here. You do a raster scan, and then you can make an image. Next, we have interferometers. And the pictures here are of the VLA in the middle and the LOFAR telescope on the right. The VLA consists of dish antennas, and the LOFAR telescope consists of a really large number of dipole antennas which work together to behave like dishes. What you measure with an interferometer is the Fourier transform of the image that you're looking at. And the effects of only partially sampling this spatial frequency domain are visible in this example image over here. So now I'd like to draw your attention to the contrast between these two types of instruments and the images that they produce. On the left, you have the single dish, which is blurry, which means it has a limited angular resolution, but it has measured all of the spatial frequencies up to that point. Whereas an interferometer can get you a high angular resolution, but you have missing spatial frequency information. So now you can play games. You can have algorithms that combine single dish and interferometer data because they're complementary. You can do things like mosaics, where instead of having each antenna essentially measure one pixel, you could put a multi-pixel feed at the apex, for example. If you do that on a single dish, you get a mosaic instantaneously, and you can make a mosaic of mosaics. If you do that on an interferometer, you can get a mosaic of images all at once. And so there are all kinds of things people do. An edge case, you can even do tomography if the object that you're looking at far away is conveniently rotating for you. And so people have made images of Jupiter's emission region by simply taking different integrated line of sight measurements as the thing is rotating. So, all right. So now let's go into how interferometry itself works. Conceptually, one can understand everything just with the Young's double slit experiment, which I'm sure everybody here is going to be familiar with. If you have a plane wave incident on a pair of slits, you get a fringe pattern, and the wavelength of the fringes depends on the spacing between the slits. Okay. Now here's a picture of the VLA interferometer. It's an array of detectors, and you can think of every antenna here as a slit. Therefore, every pair of antennas is sensitive to one different fringe pattern. And if you can measure them, you can simply add them all together, and there's your Fourier series or a Fourier transform. All right. So conceptually, this is how you make an image. And so the goal here is to measure as many different fringe patterns as possible. What do you mean by measuring a fringe pattern? There are 4 parameters that describe it. There's the amplitude and phase, and the orientation and its wavelength. So how do we get that number? The basic measurable from an interferometer is a measure of the spatial correlation of the E field incident at each pair of antennas. So if you have 2 antennas described by these blue things here, and you have a source from a certain emitting radiation that's coming from a certain direction, the plane wave hits the first antenna J first, and then gets to I with some delay. So what you do in the electronics is you actually on purpose delay one of the signals so that by the time they can be combined, they are in phase with respect to the direction that the instrument is pointing. And then we do what's called a correlation, which is just a multiplication of the 2 E fields or voltages integrated over time. So it's integrated over a finite time and a frequency. We have n antennas, and therefore n times n minus 1 over 2 such measurements at any given frequency and time. Now, what do we do with this? This EIEJ star is a complex number. And so that is what gives us the amplitude and phase of those fringes, for the fringe pattern for this pair of antennas. And everything else, the orientation, the wavelength, comes purely from geometry. To say this a little more formally, we have the Van Sittert-Zernike theorem, which is a far-field equation. It relates this particular measurable to the Fourier transform, the 2-dimensional Fourier transform of the image on the sky. And that's called the visibility function. And therefore, in the rest of my slides, I'm going to say visibilities. And all it means is our measurements on the k-space, essentially. And I'd like to highlight at this point that this is a 2-dimensional equation. But in its general form, it has the form, it's what's shown in the green box at the bottom. And the reason I put this here is because when you go to Dan's talk next, you're going to see exactly the same functional form. Completely different physics for MRI, but you get to this exact same functional form. And so I want to highlight that. All right. So now we have these EIEJs. how do we fill in our K-space or UV space? So that's the next couple of slides. So the pictures here on the right show drawings of the K-space, our K-space, which we call the UV space, and the corresponding fringe or image. If you have a pair of antennas, the projected distance between them is essentially what's encoded in the location of this, where this complex number is placed on this grid, as shown here. And there are two spots here. One is one spot and its complex conjugate. And there are two of them because a real valued image has to have a Hermitian transpose. And so it's details like that. Now, as a function of time, the Earth rotates, which is equivalent to saying the sky rotates over the Earth, which means the projections all change, which means as a function of time, the same pair of antennas can give you a different baseline, so to speak. And that can look like this. And so at another instant in time, you can get another measurement and put it in a different location on this plane and get another fringe. And this is how you build up. And of course, different pairs of antennas are also going to give you different locations. So here's a little animation now to show how this builds up in practice. The picture on the top left, it represents a true sky, the truth. And the two pictures on the right are the UV plane or the K-space plane and the observed image. And so this is the image formed by two antennas, so one baseline and its complex conjugate. And as you increase the number of antennas, you can see your UV space or K-space filling up, and you can start to see structure on the right-hand side. This little matrix on the left essentially shows how you can translate the various parts of the pieces of the geometry to the locations on this UV plane. And so far what I've shown you are how it changes when you keep adding antennas. Next, you can wait for the Earth to rotate and use the rotation and the projections. And so you can fill in even more space. And this is called Earth rotation synthesis. You can go one step further because this is optics. And all distances are measured in units of observing wavelength. So by changing the observing frequency or wavelength, you can get even more coverage. So by the time you get to this point, this is the best that the instrument can do. And if you do just a direct inverse imaging, this is the image you'll get. It clearly shows the sources, but there is also this characteristic pattern sitting all around them. And that is, of course, our point spread function. And the point spread function encodes several key imaging properties of the instrument, such as the angular resolution, the side lobes indicate how many gaps you have in the spatial frequency coverage and other things. And the point spread function is directly the Fourier transform of the coverage. So anyway, and the other thing you can infer from just looking visually at the plot on the right is that the observed image can be represented as a convolution of the true sky with this pattern, right? And so let's keep that interpretation in mind. So let's go to getting a little bit more formal. Here's what in interferometry we call the measurement equation, which is equivalent to saying it's the forward problem. And we have the image and the two-dimensional Fourier kernel, a sampling function, which gets essentially multiplied onto the Fourier transform of the thing during measurement, and another term, which I'm going to call as direction-independent gains. So let's see what these are. When we make a measurement, what we would like to measure is just the incident E fields and how they correlate together. But what comes for free is additional multiplicative complex factors that get applied one antenna at a time or per antenna. This is sort of a catch-all for all kinds of effects, but you can generally model it as a complex number that multiplies with the incoming E field. So what comes out of the correlator, which is what is recorded in our data, is not just the EI EJ that we want, but it has this GI JJ star along with it. And so we have to undergo a process of calibration to first solve for these G's because they are also unknowns, and then divide it out. Now I'll leave it ambiguous here as to how you solve this because there are multiple ways. You can use a known source or a calibrated source where the E's are known, and then you can solve for the G's and take it out. Or you can even solve for it at the same time as solving for your I itself. And so there are various ways of doing this. But that's calibration. Okay, and that is essential because only if you do that can you get the numbers such that they satisfy Fourier optics that you can then take into convolution equations. So once you're done with that, now you can deal with the rest of this equation. So step one is to make the image. And this is the inverse imaging problem. And inverse imaging essentially is a gridding step, an inverse Fourier transform, and an appropriate normalization. Gridding is a process that we use to take what is an analog distribution of data points in UV space and put them onto an actual grid so that you can use an IFFT. And in practice, it looks something like this. This graph shows a set of grid cells on the UV plane. And the blue track is the continuous analog track which is traced by a baseline. And the small green circles are where you actually have measurements. And so we do the interpolation by a convolutional resampling, where we take a gridding convolution function, place it at the true location, and simply read off the values at the grid cells and add them all together. That's basically what gridding is. So once you do this and you make your observed image, you can then now interpret what this might be. And this is again what I described a little earlier. It is you can interpret it under some approximations as a two-dimensional convolution equation. So the observed image on the left is a convolution of the point spread function with the true sky. And it is this interpretation that allows us to frame the image reconstruction step as a deconvolution. Traditionally, or rather the way the field has evolved, it has been these physical interpretations of the equations that have driven the algorithm development. And the field has only more recently moved to more formal numerical math and optimization language definitions. And so that's an interesting direction of evolution. And as I understand it, in the medical imaging side, it's almost in the other direction. But anyway, for us, in this simplified two-dimensional regime, our image reconstruction is to solve this convolution equation. All right, so here's what we have so far. Now, this is not the entire story. The actual expressions look something like this, which have many more terms in, and you immediately see that the two-dimensional Fourier transform no longer exists. At this point, I'd like to pause a little bit and just again draw your attention to just rewrite this in its most general form. And this is where I would like to again ask all of you to connect to what you're going to see in Dan's talk coming up later, because again, the functional form is identical. So here on the top is the simplified version, and at the bottom is this term where you now have other effects that are multiplicative in the image domain, and you also have other effects in the phase term of what used to be the Fourier kernel. This is a phase term. It could be either in here or it could be as part of the M. It depends on how you choose to model it, but the structure and functional form is the same. And this is where, going forward, this is where there's a lot of interesting overlap in the solution techniques, because completely different physics, we have all come to exactly the same problem, even in its most general and complex form. All right, so I'm going to give a few details of what these actually mean. So we have the usual direction independent gains, and I'm going to say a little bit of what these direction dependent effects are and what this jargon of W term means. An interferometer has multiple antennas, and each antenna itself has a response pattern. It's an antenna gain, right? And in the direction that it's pointing, there's also going to be the ionosphere and the atmosphere and all kinds of other things which can cause additional refractions. So how does this relate to these M's up here? The direction independent gains, which I described earlier as the G's, come not only from the electronics at the back of the antenna, but they also are representative of the absolute forward gain of the antenna, right? And it's a single number per antenna. And that's why it is direction independent. Direction dependent effects are the actual shape of the antenna. If you assume the peak to be 1, what's the actual shape of the rest of it? And also it encodes refractive effects because they change across the field of view here. Mosaics are another thing here, which essentially tells you where the dish is pointing. All of these things are encoded in here in this M. Okay. So that's for the M's. What's next? The sky brightness. Now, ideally, the two-dimensional Fourier transform has a sky structure that is not changing with time or frequency. It's just the same. But in reality, it changes with time and frequency. As if I show the same examples that I showed much earlier, that you can model the spectrum change. The spectrum is smooth in some cases, and you can sometimes model that along with the solution process and do a joint reconstruction across frequencies and derive images that look like this, where you can encode color and intensity that mean different physical quantities. And of course, all of this can change with time. The basic algorithms we have do not really support it, but there are prototype algorithms out there which do support it. And in fact, I'm sure we'll hear more about this in one of the next talks as well. Finally, what's this W? This W term is an entirely geometrical effect, and it's related to the far field versus near field difference between the two fields. So on the left, we show a plot of two antennas, not a plot, a figure with two antennas pointing up and phased up. And it relates to the fact that the sky is actually curved and not a flat image. And so if you get, the further you get away from where the instrument is phased up and looking at, the fact that what you're looking at is not flat starts to matter. And that's this n coordinate here, which comes into the equation up here. Another way to look at this is that if your antennas are looking up and phased up to the top, the wavefront from a source on the side does not hit both the antennas at the same time. Obviously, it's going to hit the first one first, which means you have to now take into account near field propagation effects between that plane and your antenna. And that's the magnitude of that is given by this W term here. And so these are both entirely geometrical effects, and they can be modeled quite exactly. And so then it depends on how well you can incorporate that into your reconstruction. Okay, so this has been a description of what is in the equation, and more importantly, the physical interpretations of those. But how do we actually solve these? The first part, the direction independent gains, we typically handle by an external calibration. There are situations where we do calibration in a loop with image reconstruction, and it's called self-calibration, but for simplicity's sake, let's keep it separate. The next thing we can do is handle all of these terms in green. These are direction-dependent effects. And the important thing to note here is that they are all multiplicative in the image domain, all right? And anything that's multiplicative in the image domain is a convolution in the visibility domain or the k-space domain. Where is the other convolution that we do in the visibilities? Our gridding process is itself a convolution. And so by choosing our convolution functions carefully during gridding, we can actually model and undo some of these effects. And so all of this is going to be covered in is covered in the bucket of inverse imaging, and which we will also be hearing about more later. Now, once you've done that, you have presumably, to some degree of accuracy, corrected out instrumental effects in geometry. And what you're left with is the nice two-dimensional Fourier transform relation again, with some caveats, but basically that. And then comes the image reconstruction, where you have to now undo the effect of the partial UV sampling function, and that's where the deconvolution comes in. So I hope this slide conveys, the whole picture, the most general expression, and how we typically, what are the parts that get corrected for at different stages of the imaging and reconstruction. And two of the later talks are going to be focused on the details of these last 2 points, the inverse imaging and the reconstruction itself. Now, beyond this point, if you notice, I've written only the forward transform. Writing the reverse or the inverse problem in this formulation gets complicated. So at some point, it becomes far more efficient to move to matrix math. You can generalize and encode all of those effects into a measurement operator, which we shall call A. And so you can write the forward problem as simply as the observed visibility is A times the I, the true sky, plus some noise. And again, I'd like to emphasize that this generic formulation is there's a direct counterpart that you're going to see in the next talk as well. So you can write the inverse problem now as simply as your best ability to invert A multiplied by your data. Now, the algorithms in radio interferometry, as I mentioned before, have sort of evolved more organically and based on the physical interpretations. But in the end, it is perfectly possible to cast them into a formal optimization framework. And if you do that, you can make the statement that what we do, and what has traditionally been done in interferometric imaging for many years, is L2 data regularization with a variety of algorithms to solve for the sky model. And different kinds of solvers and optimizers are possible. And we use, say, one instance of this. So the way this looks like in practice is shown by this diagram here. What we have on the left, and by left I mean the big red box, is the place where we do the forward and reverse transforms. And what we have on the right in the big green box is what's typically called the image reconstruction, and that's done in the image domain. So The particular formulation that interferometry uses in practice most of the time is a very simple minimization of chi-squared. And so the calculation of essentially the gradient of the thing you're minimizing is what's done in the forward and reverse transforms, is done along with the forward and reverse transforms. And the image reconstruction part is treated almost as a slightly separate independent regularizer that operates within this larger loop. So the the corrections for direction dependent effects, as I said, that can be done during degridding and undone during, can be done during gridding and undone during degridding, so that you complete the forward and reverse transforms properly. On the right-hand side, there are a variety of algorithms. You can model the sky as delta functions, as Gaussians, as wavelets, shapelets, name it. And there are a variety of algorithms that go and model those as well. The one most commonly used in production operations is the clean algorithm, which is a very efficient, greedy algorithm that works in most cases. But improvements on that, there are a large variety of algorithms and compressed sensing ideas and all kinds of things. And I'm sure we'll hear more about these in the next couple of talks as well. All right, so in the last few minutes, some summary information. What limits us? And this is a topic that came up in the previous set of talks. So I thought, let's both sides describe this. So the first is signal to noise ratio. You do have to have enough measurements so that your noise goes down, is beaten down enough so that your signal actually pops up. Everything that we do in ideal conditions can be modeled as Gaussian random noise. And so it's basically a matter of getting enough data so that you can beat down the noise so that your signal sticks out. Right? The next is angular resolution and sensitivity. And there's just a picture to show you what you mean over here. The image on the left is one that has a low angular resolution, but the same source shows up much brighter. And on the right, you have exactly the exact same data imaged or taken with the telescope at a different angular resolution, and you can see the contrast is a bit harder. So when you're making an image, you have to now target your observation to what kind of a science you want to get out of it. Are you interested in just detecting something, or are you interested in the very small detailed structure? And those sort of intents will guide what kind of an instrument and how you set things up. You often cannot get both at the same time, and then that's where joint algorithms come in to try to get the best of both worlds and so on. Dynamic range is another thing that limits us, and the two pictures that have just appeared show the effects of two different algorithms on the same piece of data. The image on the left has a dynamic range of a few hundred, which means there is a bright spot at the center, which is only 100 times brighter than all of these errors around it. Whereas the image on the right shows the same data where the central source is now cleanly modeled and modeled well, such that everything else shows up. And the dynamic range, which is the ratio between the peak of the source to the noise level out here, is 100,000. So this is just to showcase that for typical sources on the sky, I mean, this is one of the brighter sources, but our algorithms need to be accurate up to 5 orders of magnitude in dynamic range before we can actually reach or even see the noise level that these telescopes are capable of producing. And so now going forward, much of the science in the astrophysics depends on being able to see weaker and weaker things. And so we are building more telescopes to get more data, to beat the noise down more, which means more and more instrumental and all kinds of other artifacts will show up more clearly, and which we are going to have to deal with in the algorithms. So that's 100,000 to 1 dynamic range is not unheard of in radio interferometric imaging. The next is an example of unmeasured large spatial scales. And this is what I referred to right in the beginning of the complementary nature between a single dish telescope and an interferometer. What you see on the left is high resolution information, but these sort of dark patches are essentially negatives. Now, power and intensity cannot be negative, right? So there's missing information there, which you can fill in if you do a joint reconstruction with information from a single dish. And this is important for the astrophysics, because since the absolute value of each pixel, the flux density, that matters, because that connects to energy budgets of the source. So you have to be careful about reconstructing all of the structure that's possible. What some science can be done by just looking at the relative structures of these things, filament shapes and whatnot. But if you're trying to interpret the absolute values, you need to make sure that you have all of the spacing information. The next one is instrumental effects and the accuracy to which you can correct them. These image pairs, the left and the right, are examples of different instrumental effects without and with correction. So the top one is what we've called the W term. If you don't correct for it, what should be, what looks like the thing on the right will end up looking like what's on the left. And similarly, the images at the bottom are, if you have good models of the antenna primary beams and antenna response patterns, you can get what you have on the right. And if you don't have them right, you get the left, and so on and so forth. The last bit of the last picture to add here is algorithmic variability, an example of algorithmic variability. This is now on the image reconstruction side. We have a variety of sky models, a variety of objective functions being optimized and different techniques, and all of them produce slightly different results. And in our case, we have no idea what the absolute correct truth is. And so there has to be some way of quantifying what variety is natural, how much can be tolerated for the science, and so on and so forth. But again, just to show, these 4 examples are made by 4 different algorithms, image reconstruction algorithms, and they are all correct in some way, but you can very clearly see that they're all different. So that's a thing to contend with. And finally, all of the above have to be handled at large data volumes and increasing computing costs. Because as I mentioned at the start, the way this is going, more data, less noise. So more data means more compute. So to summarize that, and this is my second last slide, going forward, data volumes are only going to increase. And I believe this is a point that is interestingly in contrast to how medical imaging has evolved and does things. Because in the medical imaging side, you have full control of the UV space and the K space. And you're looking to get lesser and less data so that you can improve on timing and you don't have to deal with people moving. In our case, we're going in the other direction. So data volumes are only going to increase. And the idea is to make image noise go down. But this means that instrumental effects are going to be more easily seen, which means you're going to need all of the more complex algorithms. You cannot get away with simple 2-dimensional approximations anymore. And that means the compute cost increases, which then means that manual data reduction and analysis becomes much harder, and people are already running into this right now. And so you need both high performance computing and automation, right? So that's where it's all going. And these are just artist impressions of what the 2 of the newest, the next generation telescopes are likely to be. And just to put things in perspective, the square kilometer array is looking at 2,000 dishes and 1 million antennas. And the next generation VLA is looking at a few hundred dishes. And in comparison, our current telescopes, which we are currently just barely able to keep up with and operate, the VLA has 27 antennas and the ALMA has 60 antennas. Okay, so this is a big step up. And so there's going to be a lot of potential for interesting solutions. What's the R&D frontier on algorithms? There are, of course, a variety of sky models that you can pick, delta functions, Gaussians, wavelets, whatnot, different instrument models, different objective functions and regularizers and optimization strategies, even differences in what you choose to encode as prior knowledge and what you solve for. And I'm sure the next 2 talks by Maxim Voronkov and Kazunori Akiyama are going to cover a lot of these interesting details. On the front of compute load, we cannot operate without parallelization, of course. And so there's more and more efforts into doing this cleanly and efficiently and in an easy to program way. The use of GPUs are only recently coming into the picture for us. And I hear that on the medical imaging side, that has already been used. So it'll be interesting to cross-pollinate there. And the last point is automation. Data in radio interferometry, people are used to reducing their data by hand. So you get a data set and you sit with the software package and then you sit and run through all the steps yourself. But as you get more and more data for big surveys or people, large volumes of data, that becomes harder. And so observatories such as ours are investing huge amount of effort in data analysis pipelines that give to end users what we call science-ready data products. As of now, these are essentially teams of human beings who design carefully tuned heuristics that they encode in a script. This is a very simplified way of a pipeline. There's much more to it than this, but essentially it's this. And that's what's used. But every time a new mode comes along, this effort has to be repeated. And so there's a lot of desire for innovation in how do you automate all of this. And sometimes that's using existing tools. Sometimes that's going all the way back to the forward modeling equations and looking at different ways. People are looking at it. but I don't think there have been any breakthroughs that are, and certainly nothing has come into production at this point, apart from the existing, human-based, heuristics-based detailed pipelines. I think I will end there. So just about end in time, and I'd just like to acknowledge a few people. Thanks a lot to Dan. We had a couple of conversations before this where we tried to make sure that these two talks align with each other, and it will be up to all of you to see whether we actually achieved that or not. Also, thanks to Sanjay, who I ran this by, and the NRA, of course, and to the organizers for allowing us to be a part of this. So thank you, and I'll take questions.
Great. Thank you, Urvashi. First question is, how does the mounting number of satellites and constellations of satellites interfere with measurements?
So that is an active topic of research and analysis on our end right now. Low Earth orbit satellites, especially for internet connections, expect to use broad bands of spectrum that we also want to use. And yes, if they do fill up all of that space, we will lose a good chunk of frequency, and so it will be a significant loss if it fills up that band. Typically, the way we handle what we call interference is by just identifying locations in our data on the time, frequency, and antenna space, and simply blanking them out and throwing them away and taking them out from further processing. And so the net effect is a data loss. And a data loss can be translated into a limit on how much your noise can go down. And so that's how that's connected. What we are currently engaged in at the observatory, actually just in the last few weeks, is active tests along with, say, SpaceX, to turn on their satellites and actually make measurements and see how this actually affects the data. And results for that are pending, but yeah, it is a big question to be answered. If we end up losing a good fraction of space, that's a fraction of frequency space, that's serious. But some models also suggest that the power levels may be such that it may not be that big of a deal for some situations. So, but yeah.
Okay, a second question is, in medical imaging, we often rely on imaging phantoms to provide a ground truth. Is there a similar reference to use for method development and evaluation for radio astronomy? And
yes.
I'm not familiar with the term phantoms, so perhaps, do you know what that means?
Yes, and I think the equivalent is what we call simulations. And it's essentially, or test observations of known things. I think that's the connection. And in our case, there are some sources on the sky that have been studied to death for many decades, and people know exactly what's in it. And so when you develop a new method or an instrument or an algorithm, you look at that as a test. But the more rigorous thing from an algorithm developer's point of view is simulations. So we put a lot of effort into essentially evaluating that forward model very, very accurately, so that given a fake or a fiducial shape or structure on the sky, we can construct data sets that mimic what the telescope will give us, and then try out our algorithms on that. And at that point, you have ground truth against which to do comparisons. So I think that is the analogy. But Dan, maybe if there's any other interpretation to the word phantom, please do chime in.
No, I think that's dead on. That's why we use phantoms.
Okay, we have one more question now. Could you make some comments on how you determine the signal to noise ratio of sources, given the peculiar properties of noise that you described, especially as criteria to stop the deconvolution algorithm?
In an ideal sense, if you have perfect deconvolution, you should be able to reach what we call thermal sensitivity. Okay, so I'll say what that is. So given an observation, if you have telescopes with dishes of a certain size, a certain number of observations and a bandwidth and all of that, you can actually calculate from measurements of system temperature and all that of the instrument. You can calculate and predict what level of image noise you expect in an ideal case, and that gives you a lower bound. That's your absolute best case. There's nothing you can do that'll get you below that. So now the question is, when you're doing your image reconstruction and calibrating your data and all of that, how well and how fast can you approach that? So in an ideal case, if it's a simple case and you've done perfect calibration and it's a simple sky model and you've done perfect imaging, you can converge towards that. And we typically use stopping criteria that are based off of this theoretically predicted and calculated ideal noise level. You can say you can stop to say 5 sigma level is how we describe it. And you stop at that point. What becomes more interesting and the harder case is when you don't actually reach that. That is, if there are other things in your data that your algorithms and your inverse imaging has not accounted for, then you're never going to reach that. So you may hit dynamic range limits, or you may hit, ionospheric refractions, which you have no idea about and you have not been able to model into your equations. And in that case, it becomes much harder to decide when to stop. And typically, when somebody is doing this interactively, you typically watch your convergence profile, and if it starts flattening it out and absolutely nothing useful is happening, you stop. And this is where the algorithm automation, the smarts for knowing when to stop come in. And so yeah, in the clean case where everything works as you expect, we have an absolute measurement of a theoretically defined stopping criterion. In all other cases, it's up to experience.
There are several additional questions showing up about automation and machine learning. So I'll ask one of them, and then I think we'll want to move on after that. But one of the questions is based, automation is a growing frontier as we deal with more data and information. So what are some of the main innovations in automation and machine learning? That's probably an entire talk on its own. So if you want to give just a brief take on it, this will be the last question.
The brief take on it is there are a large number of people trying various things, but nothing has hit the news. Let's put it that way. Yeah, I'll leave the details of that to some of the later talks if people want to talk more about this, but or additional discussion. But there are several groups trying out different approaches. And here is actually another area where I, just in 2 conversations with Dan, suggest that, I'm hopeful that some of the ideas that have already been shown to work from the medical imaging side, we may be able to just borrow. So I'm very curious to see how that goes.
So thanks again, Urvashi.